Hi, let's take up some paradoxical oxidation numbers in this video. In the previous video, we had seen how to determine oxidation number by using some simple rules, and also we had understood what is the concept of oxidation number, where from it has originated. But let us apply to some tougher molecules, tougher ions, and you promise me if you cannot understand some bond structure, you don't complain. Just take it as such. When you study chemical bonding and you will be very conversant with writing the Lewis structure, then it will be very easy for you at that time. But for now, if you have understood it, if you will understand it, it's well and good. If not, also well and good. Take it as an information, right? Let us start some paradoxical cases where the value will be coming fractional, or it will be coming something which will not be a true oxidation number of an atom. That will be the average, merely an average. We will be discussing a few cases. You might encounter with many other cases, but let us to give you an idea that you must always not be complacent with the rules. As a promising student, you must view a molecule critically, particularly when you find more than one atom of a particular element is present. So unless you know the bond structure, you say that the value you got from the rule method is merely an average value. Okay, let us start. Okay. Now let us take some critical cases. Paradoxical oxidation number means calculation based on rules sometimes results oxidation number which is unconvincing, particularly when it is fractional. It just gives an average oxidation number value. How can it be fractional? Electron is shared. Either it is transferred. It is transferred. Either it gains 1 electron, 2 electrons, 3 electrons, or loses 1 electron, 2 electron, 3 electron, and so on. It has to be a +2, +3, +4, or -1, -2, -3. How can it be fractional? So if that comes, then you have a strong suspicion that it's not the true oxidation number. It is merely an average. Sometimes the oxidation number doesn't agree with their positions in the periodic table. For example, if sulfur you are getting by formula method, by rule method, you are getting sulfur oxidation state +7 or +8. Can you believe it? Can you believe the sulfur can lose maybe theoretically 7 electrons, 8 electrons belonging to group 6A, group 16. It has 6 electrons in the valence shell. If you have already studied, sulfur, oxygen have 6 electrons in their valence shell. So how it can lose 7 electrons or 8 electrons? So here is the paradox. It appears as if it is +7, but it is not convincing. But actually when you draw the bond structure, or you know how to draw the bond structure, you will be convinced, no, this is not +7 or +8. It has to be maximum +6. Cannot go above +6 because it has 6 electrons, either to share or to lose, though in a theoretical manner. Because oxidation number is a theoretical concept, I told you. In some other cases, the actual bond structure gives a different actual oxidation number, although it will be coming apparently convincing, not exceeding the group value, group number, but still, and not fractional, still it is not correct. In that case, you have to know the bond structure. The different actual ON value can be determined from the bond structure, which will not match with the average value calculated, even though the value is not fractional and doesn't exceed the group number like the case I cited. Now, I will give you more than one examples of each type. Let us take. This is called sodium pentasulfide. Carefully listen to me. Sodium pentasulfide. So at first sight you may think sulfide is a monoatomic radical, so -2. So for 5 atoms -10. So 10 by 2 plus 5. Can you believe sodium can have ever any variable oxidation number other than +1? Never ever possible. So you must think that this is a different kind of sulfide. This is called polysulfide. Polysulfide is written like this. It is like this. Sn 2 minus, all 2 minus. Whether it is disulfide, trisulfide or pentasulfide, all 2 minus. So these come under polysulfide category. So what you get will be fractional. For example, we find by X method, this is sodium is +1 for 2 plus 2 plus 5x is equal to 0. So we get X is equal to -2 by 5. So you can write that, no harm. But if you are asked, is it really has any sulfur in the ion or in the compound an oxidation number of -2 by 5? No. You will merely say it is an average value. If I draw the structure, you will tell me the oxidation number of each sulfur atom. Let me draw the structure of this pentasulfide for you. This comes under polysulfide. This is a chain of sulfur atoms. And this terminal carries a -1 charge. This terminal also carries a -1 charge. And all others are connected in series. Now tell me, if the atoms are same, then there will be homolytic cleavage. So if there will be homolytic cleavage, each gets back its own electron, then there will be no charge developing on the internal sulfur atom. All of them will have an oxidation number of 0. All these three. But this one is already -1. It has got from sodium, so that it is already having an oxidation state of -1. And this also has an oxidation state of -1. From this direction, no electron gain or loss. From this direction, no electron gain or loss. So the -1 that it is having, it is only due to some other fellow which has lost electron, right? So this is -1, this is -1, these three are 0. So if you add all the charge, total charge is -2, and all the 5 atoms, is it not the average value? So that we are getting in our formula rule method. So this is a paradox. Looking to the value of oxidation state that you got by using the rules, it will be highly unconvincing. Once you understand the structure, you can assign the oxidation number to each atom. Let's say this is called red lead. If you find by X method, then it is 3x minus 4 to the 8 is equal to 0. So X is equal to plus 8 by 3. So this, but undoubtedly you cannot believe it. How can lead have a fractional, or in fact any atom can have fractional oxidation number? This is unbelievable. So if you know, possibly many things you are not in a stage to know, as time proceeds, as more and more information will be loaded onto you, then you enrich your experience and know many things. But so don't be discouraged if some more information is loaded onto you. Take it as an information. This red lead is nothing but 2 lead 2 oxide and 1 lead 4 oxide. This is a double compound. 2 PbO, there are two molecules, in the ratio 2:1, lead 2 oxide and lead 4 oxide. Plumbous oxide and plumbic oxide are there in the ratio 2:1. So it is, you just add, you will find it is Pb3O4. Now, In PbO, the oxidation number of lead is +2 because it is a monoatomic ion. And in PbO2 it is +4. This is lead 4. So if you add all and take the average for 2 lead 2, so 2 2s are 4 plus 1 lead 4 plus 4, and how many atoms are sharing? 2 plus 1 3. So is it not the average that you got by using the rules? Yes. So actually plus 8 by 3 is not the oxidation number of any lead atom. All the 3 lead atoms, out of the 3 lead atoms, 2 lead atoms have an oxidation state of +2 each, and another one has oxidation number of +4. That's the reason why you are getting plus 8 by 3. Got it? Similarly, this is called magnetic oxide, or some people call it a ferroso-ferric oxide. Again, by X method, 3x minus 8 is equal to 0. So X is equal to plus 8 by 3. Similar to the red lead. Plus 8 by 3. You may write down, no harm. But it is unconvincing, it is paradoxical ON. So when you know Fe3O4 is nothing but a combination of ferrous oxide and ferric oxide in 1:1 mole ratio. You will know subsequently in your solid state program that it has got a very typical solid state structure. I am not going to discuss its solid state structure now. So this is ferrous oxide, 1 mole ferrous oxide, 1 mole ferric oxide. So tell me, in ferrous oxide, this is iron 2 oxide, this is +2. And this is iron 3 oxide +3. So what is the total oxidation state number? Is +2 and 2 of iron 3 type. So +2 +6, because there are 2 iron atoms having +3 state. So total is +6 divided by the number of atoms sharing is 3. So the same answer you are getting as you did in a rule method, plus 8 by 3. But none of the iron atoms has an oxidation number plus 8 by 3. One has +2 and 2 have +3 each. You understood what I am talking of? Paradoxical ON. Oh, by rule method you will get some value which will be unconvincing to you. So that is a paradox. Now, tribromine octoxide. Tribromine octoxide is a very typical molecule. By X method, you know what you are getting. Bromine, 3x minus 16 is equal to 0. So X comes plus 16 by 3. This is highly unacceptable. Unacceptable. Then you have to know the bond structure. Once I draw the bond structure, in a flash you will tell me the oxidation number of each bromine. Will I? Let me. This is the bond structure. You may be wondering now, because you are a beginner, I am sure most of you have just crossed class 10 examination. If so, then you must be wondering how to know all these bond structures. The answer to this query from my side is, don't worry, stay cool. Just get this as an information. What are real oxidation number and what are paradoxical ON number? That concept you be clear. That's it. Now let me draw the structure, and I'll ask you to stop the video at that moment and calculate and find out, not calculate, find out what is the oxidation number of each bromine atom. This is the structure. This is a very symmetrical molecule. 3 oxygen atoms on the 2 terminal bromines and 2 oxygen atoms on the middle bromine. You just forget if you are little apprehensive of so many double bonds. Just stay cool. Don't worry about it. How octet rule is violated. So you just stay cool. Chemical bonding is a huge program that you will be studying in due course. Now you tell me, after looking this structure, tell me what is the oxidation state of this, this and this. I give you, you pause now. Pause the video and calculate. But I will continue with my discussion, but you pause the video, okay? Now this will be having, if this will be losing 2 in this direction, 2 in this direction, because bromine is less electronegative, oxygen is more electronegative, so 2 in this direction. But this, there will be no gain, no loss, because the two are identical. This will be homolytic cleavage. So 2 plus 2 plus 2, this will be plus 6. So this will be plus 6. Similarly, this will be plus 6. Same. These two, these two, these two, 6. And this is homolytic cleavage. And what about the middle one? This side homolytic, this side homolytic. Only 2 to this side and 2 to this side. So it will lose 4 electrons. So this will be plus 4. So the two terminal ones plus 6 and the middle one plus 4. Therefore 6 plus 6 plus 4. So 16 by 3. So the average oxidation number comes 16 by 3 that you wrote. Unless and until you know the bond structure, it's not possible to assign the oxidation number of each atom of a particular element. So never ever mind that you do not know this structure. You will know subsequently. Now this is called carbon suboxide. Like carbon dioxide, carbon monoxide, this is called carbon suboxide. C3O2. So if you find by rule method 3x minus 4 is equal to 0. So x is plus 4 by 3, fractional. So you cannot believe it. This is merely an average value. So then I will tell you the structure of carbon suboxide, and you will now tell me what is. Now see, there is a trend. Carbon, 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 all are doubly bonded. And there are 2 terminal oxygen atoms. Now tell me, what will be the oxidation number? Pause the video, find for yourself and then match. This. Done? Now, let me, after a while, let me see you. Now, what about this? What about this? Middle one. What about the middle one? Tell me. It is 0. Why? This side homolytic, this side homolytic. No gain, no loss. 0. And what about this? From the left side there is no gain, no loss, but it will lose 2 electrons to the 2 electrons to oxygen atom. So this will be plus 2. Similarly, this one will lose 2 electrons to oxygen atom, plus 2. So the net charge will be plus 4 and the number of carbon atoms shared for average is 3. Therefore, you are getting plus 4 by 3. But none of the carbon atoms has an oxidation number of plus 4 by 3. 2 of them have plus 2 state and one of them, the middle one, is in 0 state. Right? Now let me eclipse myself. Now this is called tetrathionate ion, as you have, must be familiarized. Tetrathionate ion. If you apply the X method, this is 4x minus 12 is equal to minus 2 because it is an ion. 4x minus 12 is equal to minus 2. So x is equal to plus 2.5. 10 by 4, that is 2.5. So that carries no meaning. How can it be fractional? 2.5. Now your turn that I will draw the structure. You will have to assign the oxidation number. This is S4O6 2 minus. Now, pause this video. Assign the oxidation numbers. So obviously, this 2 will have 0. The middle ones will have 0 oxidation state because homolytic cleavage on both the sides. But this sulfur will lose 5 electrons, 2 for this double bond, 2 for this double bond, and 1 for this single bond. So this will be plus 5. Same is the case with this one, plus 5. 2 here, 2 here, 1 here. So plus 5, 0, 0, so total is plus 10, and there will be 4 sulfur atoms which will be sharing for average, so you are getting plus 2.5. Plus 2.5 is nobody's oxidation state. 2 have plus 5 state, 2 have 0 state. Now let us talk of triiodide ion. Triiodide ion, if you find X method, 3x is equal to minus 1, so x is equal to minus 1 by 3. So this is minus 1 by 3 each. But how can it be minus 1 by 3? Let me draw the structure. This is the structure. Forget about the Lewis structure. You are not supposed to know the Lewis structure at this stage. Supposing I do it like this. Now tell me, this homolytic cleavage, all are identical. So this 0, and the middle one is already having minus 1 charge. So the only one, middle one will be minus 1, and the terminal ones will be 0. So minus 1 will be shared by 3 atoms, so it is minus 1 by 3. Understood? Am I going well? Is the course going fine? Are you following me strictly? If yes, good. Now, let us talk of once again thiosulfate ion, which I did tell about in the beginning, in the previous video, thiosulfate ion. Now, thiosulfate is similar to sulfuric acid in structure, and in X method we already know 2x minus 6 is equal to minus 2, x is equal to plus 2. This is plus 2, but it appears as if each of them has plus 2. But be suspicious, just like a police officer. Do not believe whatever you are getting by rule is to be correct, particularly when there is more than one atom of a particular element, right? So you have to look to the structure, and you tell me, we have done it in the previous video, might have forgotten, you tell me, this is thiosulfate. This is thiosulfate ion. I am not putting the lone pairs, forget it. Then tell me, what about this sulfur? What about this sulfur? You pause the video. This is 0 because this is homolytic cleavage. They two are identical. And this central sulfur will not gain or lose from the side of the terminal sulfur, but it will lose 1 electron to this oxygen, 1 electron to this oxygen, and 2 electrons to this double bond oxygen. So the central sulfur will have an oxidation state of plus 4, and this is 0. So plus 4 plus 0 by 2, therefore you are getting an average of plus 2, but actually none of them is plus 2. One is plus 4, the central, and the terminal sulfur is 0. Then I will take a few more cases before I finally wind up this particular lecture. This is called peroxydisulfuric acid, or called persulfuric acid, or it is also called Marshall's acid. Peroxydisulfuric acid or persulfuric acid, or it is Marshall's acid. If you calculate by X method, you will be totally disillusioned. It's not fractional. It is something which is totally unacceptable. Hydrogen 2, so plus 2. Sulfur 2 plus 2x. Minus 16 is equal to 0. So you are getting x is equal to plus 7. But can you believe sulfur can ever lose 7 electrons? It has only 6 electrons. So it is unbelievable. So something is missing. Then you investigate to its structure. You have a suspicion, here is a peroxy. Peroxy means there is a peroxy linkage where the oxygen atom is minus 1 each. So this is the structure. Have a look and tell me what will be the real oxidation state of H2, S2, O7, 2, 3, 3, 8, I'm sorry, 3 plus 3, 6 plus 2, 8, S2, S2, O8. This is peroxy disulfuric acid. Now this is the peroxy linkage. And this bond will be homolytically clipped. This bond, only sulfur will lose 1 to this, 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 1 to this. So sulfur as usual will be losing 6 electron, will be plus 6. So this sulfur also in the similar manner will lose 6 electrons and will be plus 6. And this oxygen is minus 1, this is minus 1 because this is peroxy group. Oh, because this side there will be no gain and loss, homolytic. This side there will be 1 gain, so minus 1, so also this minus 1. So that is because we are treating all the 8 oxygen atoms as normal oxide, minus 2. That's the reason why we are meeting an error. Paradoxical, completely unconvincing ON. Now, if you write disulfuric acid this like this, H2, S6, O2. This O2 is peroxy and 6 oxygen. I'm so sorry. S2, S2, O4 and O2 like this. 4 oxygen atoms are a normal oxide type and 2 are a peroxy type. Then you apply your rule for 2 hydrogen plus 2 plus 2x and for 4 oxygen minus 8 normal oxide and for both these 2 oxygen peroxy it is minus 2. O2 2 minus. This is the 2 oxygen forming the peroxide ion. So O2 2 minus. So minus 2 for the 2 oxygen atoms is equal to 0. So you will definitely get plus 6. Right? So the trick is, I tell you the trick. If by chance, by rule method, if you are getting an oxidation number which is exceeding the group number, sulfur has a group number of 6 in the old nomenclature, 6A, 6. Then if you find it is coming greater than 6, 7 or 8, so you just drag back to the group number. It has to be the group number, nothing above that. So when you drag the number, you don't say it is plus 7, plus 8, it has to be plus 6. And by chance, if you know the structure, you can convince the question setter, question poser, who has asked you the question, yes, both the 2 sulfur atoms has an oxidation number of plus 6. And the inner 2 oxygen atoms are not the normal oxide, they are peroxide. Right? Similarly, S2SO5, this is called the this is peroxy disulfuric acid, this is peroxy monosulfuric acid or Carrot's acid. This is peroxy monosulfuric acid. Similarly, there will be 2 peroxy type of oxygen. If you find by X method, it will be coming plus 8. How can you believe plus 8? This is plus 7. So you have to cancel it and write plus 6. Also you cancel this and write plus 6. But if you draw the structure, it will be clearly convincing. This is S2SO5. There is a peroxy. These 2 are minus 1, minus 1. Then when you look to the sulfur atom, it will lose 6 electrons, it will be plus 6. So out of the 5 oxygen atoms, 3 are of normal type and 2 are of peroxy type. So if you know that, then even by X method you will get plus 6. Or else you have to look to the structure where sulfur is losing 2 electrons to the top side, 2 electrons to the downside, and 1 to the left, 1 to the right, so plus 6. Now coming nitrous oxide is a very typical example where you get a funny, a unacceptable oxidation number by X method. So N2O, if you apply the rule 2x minus 2 is equal to 0, so X is coming plus 1. So you write plus 1, any examiner will be happy. Nitrogen has an oxidation number of plus 1. But does each of the nitrogen atom have the oxidation number plus 1, or it is an average? That you can know once you peep into its structure. This is the structure. Here is a typical bond that is called dative bond. You will know later that this dative bond nowadays is shown by a normal aroma, a normal bond with a plus sign on the donor and minus sign on the acceptor. Nobody is giving an arrow mark, but since you are a beginner, I am giving you the arrow mark to indicate that this is a coordinate covalent bond or a dative bond. That means these 2 electron pair belong to nitrogen, not one of them is oxygen and one of them nitrogen. That is a normal covalent bond. But this is a dative covalent bond, means both the electrons belong to the donor, right? Now tell me, when the cleavage will occur, when separation will occur, then this is homolytic cleavage, this will have no charge. And from this side there will be no charge, but both the electrons will be lost to oxygen. Both the electrons belonged to this nitrogen and both of them will be lost to oxygen. So it will be plus 2. So one is 0, the other one is plus 2. So the average is coming plus 1. But none of the nitrogen atom is plus 1. Similarly, you will be totally frustrated if you look to chromium CrO5. You can call it chromium pentoxide, but actually it is chromium diperoxide. Diperoxide is, in fact, 1 oxygen is normal and 4 oxygen atom belongs to the peroxide category. So if you find the oxidation number by X method, X minus 10 is equal to 0, then you will get X is equal to plus 10. Then people will laugh at you. Oxygen belongs to 6b or now 6. There are 6 valence electrons. You will know in future 4s1, 3d5, altogether 5 that can be at the most be shared or lost. Cannot exceed 6. Its group number is 6. So definitely there is something, some is missing, because the structure you do not know. Structure, if you know, it is very funny structure. There is one peroxide linkage here, a cyclic, and another cyclic, and normal oxygen is this. So this is minus 1, this is minus 1, this is minus 1, this is minus 1, this is minus 2. And chromium will be losing 6 electron to the 6 sides. There is a double bond, 2 electrons, 1, 1, 1, 1. So chromium as usual will be having oxidation number of plus 6. So the knowledge of bond structure, what I wanted to impress upon you, the knowledge of bond structure is also equally important to assign the configuration, oxidation number correctly. Now this is what we call bleaching powder. Sometimes we write like this, CaOCl2. In many books I find the bleaching powder formula is written CaOCl2. Just they have added. But actually this is calcium hypochlorite and chloride. Chlorohypochlorite. You can call it calcium chlorohypochlorite. So there are 2 negative ions. So bleaching powder is made up of 2 negative ions. One is hypochlorite ion and one is chloride ion. You have to find out separately. One chlorine is in a hypochlorite ion. You can apply the X method. You can get Oxygen is -2, chlorine is +X, is equal to -1 because it is an ion, so X is equal to +1. So here it is +1. And chloride ion is a monoatomic ion, so its charge is -1 and hence its oxidation number is also -1. Chloride, monoatomic ion, so this is -1. And therefore, when you find by X method in this formula, then you will get chlorine oxidation number is 0 because calcium is +2, oxygen is -2 and 2X is equal to 0. So X is coming 0. So none of the two chlorine atoms has 0 ON. One is +1 hypochlorite and the other one is -1 chloride. Similarly, this is a very typical molecule. This is called the fool's gold. It looks like gold color, fool's gold, and this is called iron pyrite. This iron pyrite, which is an ore of iron, which is a mineral, of course mineral. Iron is not extracted from this iron pyrite, mostly from hematite and all that. So this is a mineral of iron pyrite called fool's gold, and also it is called iron disulfide, iron 2 disulfide. In the beginning of this program, I was talking about polysulfide category. Here you will be cheated. You will be deceived. You will be saying that is normal sulfide, iron is in the +4 state and sulfide is normal -2. For 2 sulfide, -4, so this is +4. But a prior knowledge is required. You may ask me how? It's because I am saying. You learn from your teachers, from book, and enrich your experience. This is iron 2 disulfide. So iron is in the +2 state and sulfur is in -1 state because S2, 2 minus. So 2X is equal to -2 and X is equal to -1. So sulfur is in the -1 state. It's not a normal sulfide. It is a polysulfide, S2, 2 minus, S5, 2 minus. So sulfur is -1. But if by X method, you take sulfur as -2, you get iron as +4. Right? So that is not the correct one. Now let us apply our knowledge to find the oxidation number in some organic molecules. Though it is funny, but still you may be asked in some examination to find out the oxidation number of an atom in an organic molecule. If you apply the X method, you will be totally frustrated. Supposing we take glucose, C6H12O6. Find the oxidation number of carbon. So it will be 6X plus 12 minus 12. 6 2s are minus 12 is equal to 0. So X is equal to coming how much? 0. So, but if I draw the structure of glucose and apply the concept, the definition of oxidation number, as we have discussed so many times, you will find each has a different oxidation number. So let us apply this for acetic acid. Just I am giving an insight. Supposing you are asked to find out the oxidation number of an organic compound, then how to do that? Draw the structure. You do not know, forget about it. Just at least know the concept. That's it. So this is acetic acid. Now tell me, focus on carbon. Carbon is more electronegative than hydrogen. Carbon is 2.4, this is 2.2. So theoretically, the 2 electrons will come here, these 2 electrons will come here, these 2 electrons will come here. So carbon will be -3. And this is carbon and carbon, homolytic cleavage, no gain and loss. So this carbon will be having -3 charge. So the oxidation number of this carbon is -3. And what about this carbon? This carbon will lose 1 electron here, 1 electron here for the double bond, and 1 electron here, and no electron for the left side. So 3 electrons it will lose, and therefore it will be having +3. So this is -3 and this is +3. But if you find by ON method, supposing I give you the formula C2H4O2 is the molecular formula of acetic acid. So you apply by X method, 2X plus 4 minus 4 is equal to 0. Just like glucose, here also you will get oxidation number of carbon is 0. but you really found the oxidation number of one carbon is -3, the other carbon is +3. Right? Similarly, ethyl alcohol. X method you get something, but the actual structure will tell you some other thing. Now, let us find this carbon. So here there will be one gain, here there will be one gain, and here there will be one gain. And there will be no gain or loss from this side. And therefore, this is as usual -3, just like acetic acid. But what about this? Unlike the case of acetic acid, here there will be gain, 2 electrons gain from this side, 1 electron lost to the oxygen. Because carbon is more electronegative than hydrogen, so it will gain 2 electrons. Should have been -2, but it will lose 1 electron. Therefore, it will be ultimately -1. No electron will be gained or lost from the left side because CC identical. So 2 gain, 1 loss, so ultimately -1. So this is -3, this is -1. So if you find by X method, you will get -3, -1. That is -4 by 2. You get -2. Fine. 2x, this is 6 plus 6 minus 2 is equal to 0. So x is equal to +2. X is equal to -2. Right? So, but each carbon has a different oxidation number. This is -1, this is -3, and this is -1. Right? Now the last one. Then let's talk a little about covalency. Nobody now bothers about covalency. Covalency is not at all a thing to be serious with. Covalent, just like electrovalency is the number of electrons lost or gained by an atom or a group of atoms that we call a polyatomic ion or a radical. Here, covalence means the number of electrons shared by an atom. Shared by an atom with other atoms in a covalent molecule or ion. In oxidation state concept, it is lost or gained. But now in covalency, it is shared. The knowledge of bond structure is absolutely required here. There is no rule. For getting oxidation number, there are rules, but here you have to know. For example, carbon dioxide is a simple molecule. Now tell me, if I draw this structure, tell me how many electrons are shared by carbon atoms with the other 2 atoms, oxygen atoms with which it is connected. So definitely this on this side 2, this side 2. The other electrons belong to oxygen. So carbon has shared 4 of its own electron, and therefore the covalency of carbon is 4. But we are not bothered about covalency. We say, what is the oxidation state of carbon? It is +4. It will lose 2 electrons to this side, 2 electrons to this side, so it will be +4. Although it is a theoretical charge, but it is more required, more applicable for studying the fate of inorganic reactions, right? But the number of electrons shared is 4. Similarly, sulfate ion, what is the covalency of sulfur? So sulfur is sharing 2 electrons this side, 1 electron this side, 1 electron this side, 2 electron this side. So it is sharing 6 electrons, so covalency is 6. But what is the oxidation state of sulfur? It is +6. So in simple molecules and ions, simply if plus and minus sign they are removed, then you get the covalency. In simple molecules and ions. But not in all. Covalency and oxidation state, they will be different. For example, in N2O, as we have already drawn, this nitrogen is sharing 3 electrons, so the covalency is 3, but the oxidation state is 0. This nitrogen has an oxidation number of +2. It is losing both the electrons. It is the dative bond. But it is sharing how many electrons? 1, 2, 3 on this side, and both the electrons belong to nitrogen. So the covalency is 5. Right? So you cannot say always oxidation state is equal to covalency without sign. In simple molecules, simple ions, yes, the number of electrons shared is same as the number of electrons lost. That is the charge, theoretical charge. But in many cases they won't. So therefore I will not ask you to give more importance to covalency. give more importance to oxidation number. Practice. I've given you. Now see, what is the application of oxidation number? In the coming video, we will be extensively using oxidation number in redox reactions. I'll ask you, giving you several examples to determine what the oxidation number was in the reactant side and what has happened in the product side to see the change in oxidation number. Let's apply at least to two reactions. Zinc plus HCl, as you know, gives you zinc chloride plus hydrogen. Zinc is more active metal than hydrogen. Active metal, so it will displace, it is lying above hydrogen in the electrochemical series or in the metal activity series, so zinc will displace. So what has happened to the oxidation state of zinc? It was 0 here, uncombined state, rule number 1, and this is a compound. So zinc is a monoatomic ion, so has an oxidation number of +2. So the oxidation number of zinc is increased from 0 in the reactant to +2 in the product. So this is called oxidation. We shall be knowing all these in formal manner in our subsequent videos. Similarly, here chlorine is -1, is a monoatomic ion, -1. I'm sorry, chlorine has not undergone any change, I'm sorry. Hydrogen is in +1, hydrogen is always +1, and here it is 0, it is uncombined state. So from +1 to 0, it is a reduction in oxidation number. So that is a decrease in oxidation number. So increase in oxidation number is called oxidation and decrease in oxidation number is called reduction. So this is a redox reaction about which we shall study. So electron gain and loss happens and we can monitor the fate of the reaction by looking at the changes in oxidation number. Look to this purely covalent molecules. This is an ionic state in aqueous solution. It remains as plus minus, and this is also ionic state in aqueous solution, Zn2 plus and 2Cl minus. So you can reconcile that yes, electron exchange has happened. Zinc was having no electron gained or lost, is 0. It has lost 2 electrons to become +2. Similarly, hydrogen was +1. It was having 1 electron deficit and it has gained 1 electron. So it becomes H, and 2 such H combine to produce H2 gas. But what about purely covalent reactants? Ammonia is covalent, chlorine is covalent, and the products are N2 and HCl. So what is the change in oxidation number? Nitrogen, you will find it is -3. Hydrogen is +1, and this is 0. So -3 to 0, the oxidation number has increased. So this is oxidation. -3 to 0. So there is a increase in oxidation number. So this is oxidation. Ammonia is oxidized to nitrogen. Similarly, chlorine was 0, uncombined state, and this is -1. So the reduction is the decrease in oxidation number. This is the reduction. So we have to presume that electron transfer has happened. So chlorine has gained electron. Ammonia, although it was a covalent bond, but as if it has been ionized during the time of reaction. It has been ionized, and nitrogen has 3 extra electrons which it loses, and each chlorine gains 1 electron. So as if electron transfer has happened. Nobody has seen, no evidence is there for the electron transfer because none of them is an ionic compound, they are covalent. But still, we presume strongly that electron transfer must have happened. Chlorine must have gained electrons, so that at least this is ionic. You can verify that. Of course, in gaseous state it is not ionic, it is a polar covalent compound, but it is having minus delta charge, fractional negative charge. So how it has happened? Only because it has gained some extra density of electron. So that has happened because nitrogen has lost some extra density of electron. So this gain and loss might not be completely transferred. It may be partially transferred, but if we understand the reaction in the light of change in oxidation number, at least a fake charge, if this is a fake charge, then also our judgment, let me see yourself, then also the judgment and the prediction of, as we shall unfold the the intricacies, the interesting aspects of this logic of reaction, more and more we will know how oxidation number knowledge will help you in predicting reactions. So this is a task for you. You will do it. I am leaving this for you, this one. This is a task. This is a structure of glucose. This is the structure of glucose. You have to assign the oxidation number of each carbon atom. By the way we have been doing, these are identical atoms, no gain or loss, same, and you see what. So these are the questions you have to do, assignments. You have to assign the oxidation number by rule method, and you have to guess which one appears to you paradoxical. You don't. Many of the examples we have already discussed. And if some we have not yet, then if you guess, no, it could be paradoxical, it is not convincing, then you say it is paradoxical. Right? So you do that and do this, and that is the end of the story. And I have already given the link below in the description box. In the description box, I have given you the link for this. But this and the previous video together, one link. So you first you solve all these oxidation numbers you find out of your own, and then you refer to the answer. Don't look to the answer unless and until you solve all these few assignment I have given you. This assignment, you may say it's not few, it is large, but still I think most of them we have already done. So you do it, practice, and then you do this for organic molecule and tally. Bye-bye. See you next time with a more fascinating aspect of our journey in LOC. LOC journey is not yet over. Bye-bye.